So who am I? I'm based in Örebro in Sweden. Just out of curiosity, can you see my pointer?
Yep.
Yes, we do. Yep.
Good. Will be handy later on. So you're Stockholm in the eastern end. You have Gothenburg in the other end. Örebro is more or less in the middle. And when there's not a pandemic going on, I hang around quite a lot in Cambridge as well, and I hope to do that again once this crap is passed. So on my CLA, I've been using LabVIEW, if I did my calculations right, for 18 years. I think I started off in LabVIEW 6.1. I think it's the first version, and I think it's fair to say that LabVIEW has evolved a bit since then. Even if it was love at first sight, it's still a hell of a lot better now than it was back then. I mostly work with hardware and software architectures, and mostly for test and measurement systems. I have been working quite a lot with RF and microwave technology and measurements in particular. I went to university in Gävle, which at the time was the site where Ericsson had their RF measurements center for the worldwide. So the university program was made specifically for them and probably by them as well. I also did parts of my studies in the University of Aveiro, so close to Luis. And I'm also, apart from LabVIEW, I'm a very big fan of agile methodologies. And I prefer saying agile rather than saying Scrum, which is probably where I've been closest to in most cases. And that's mostly because if you say Scrum, you will always have that guy that said, "Oh, it doesn't work." And when you start asking, turns out it was the management forced them into having the whiteboards and having post-it notes, and they called it Scrum. And when that didn't work, Scrum was shit. And on the other hand of the spectrum, you have the almost religious Scrum fanatics that lives and breathes all of the ceremonies within the methodology. And if you're lucky, they might actually also contribute to the development, but it's more of a side project to them. And I try to be somewhere in between. We're more pragmatically using it to push people together and make sure we plan together and leverage the team's different specialities and knowledge. I've been working in a couple of different industries, and among them I have medtech and automotive, defense and aerospace, and telecom. And if you want to get me off talking about work or stuff I've done, a list of things that might throw me on other thoughts is talking about my kids, or swimming, mountain biking, or cooking. That's the things I most likely do when I'm not working. A quick look at the agenda. I'm going to give a background to why I got interested in synthetic instruments and why I started looking into it. Some definition of what makes an instrument synthetic and what doesn't make it. A few use cases where I think you should consider making your test system synthetic, and a few technical tricks to make more use of the hardware you already have, and well, make you trying to shrink your system mainly. Yeah, and back to the questions. I think unless there's something very, very unclear, I think I would prefer having the questions afterwards. So a background. So why I started thinking about synthetic instruments. I was working for a company in the aerospace and defense industry, where I think it's most common to find the automatic test equipment, or ATEs, that are rather big, bulky, and they're usually meant to handle 30 to 40 different test objects and a very wide variety of domains. So in our test systems, we had everything from low voltage to high power, low frequencies to microwaves. Yeah, look, a big difference in domains. And it tended to, when we developed a new test system, we tended to inherit things from earlier testers, of course, save energy and time. But it also meant we inherited the same instrumentation or equivalent instruments. And if we added functionality, we added instruments. So some of the systems were up to 5 or 6 full size or full height 19-inch racks, big, cramped with instruments. So space in the workshops were starting to become an issue, and obviously hardware costs were quite significant for a test system. Another thing is the life cycle and obsolescence issues you see in that industry, because the test system tended to live for 30 to 40 years, and replacing instruments that are 40 years old are quite tricky. It also a big cost. Validating a test system or a test program is very costly, so you want to avoid that at all costs. And if you switch an instrument to the same instrument or something equivalent, you might not need to validate the test program, because you can argue that it's the same thing. And I guess that's one of the reasons there is a market for very old instruments still, even if they're used. We also had something, in lack of a better term, I call it overkill in instrumentation. And what I mean by that is, for some measurements, they were only available in a certain instrument, which had maybe 100 different functions, and we needed 2. So the hardware was quite expensive with just those 2 measurements. And also, depending on the application, you might have very different precision requirements. And by application, I mean for R&D, you want to have very high precision, because you want to fine-tune your product before releasing it to production. While on the other end of the spectra, you might have a maintenance guy who wants to go into the field somewhere and want to have something that's handheld, and maybe just make sure there is a signal there, not necessarily know how it's very precise in accuracy, but you want to make the same measurements. It would be handy to not having to invent the wheel and reinvent the wheel to add for the different settings. And then there's the issue of redundancy. So if you look at my beautiful ATE there on the right hand side, all of them have their own power supplies. All of them have their own CPU, and most of them would have an analog to digital converter or digital to analog converter. And obviously all of them have a case and a display. There's a lot of redundancy there that would make it possible to make it smaller. So that's part of why I started to think that it should be some other way we can do this. And I went to the Auto Test Con in the States many years ago, and I think that's the first time I heard the phrase synthetic instruments. I don't remember who held that presentation, unfortunately, but that started to planted a seed. And I've taken the definition of a synthetic instrument out of the book called Synthetic Instruments by Chris Nadovich. And if I'm not mistaken, I think he's the one who coined the actual phrase synthetic instrument as well. So the definition is that the synthetic instrument is a measurement instrument that performs specific synthesis or analysis functions using specific software, but running on a generic, non-specific physical hardware. And I think that sums up the concept quite nicely. What we didn't want to do is find ways to use a generic hardware and ideally make all of our measurements functionality, all the personality of your instruments in software. So we're not dependent on a specific hardware to acquire our signals or to generate our signals. So just a distinction here too, because you can easily say that a synthetic instrument is a variation of a virtual instrument and vice versa, and it's partly true, but there are some things that are distinctive for the different concepts. So if you look at a virtual instrument, you have your device on the test in the bottom, and you connect domain-specific instruments. So you have your spectrum analyzer, you have a multimeter, and an arbitrary waveform generator. And you talk to the spectrum analyzers through a specific driver for that analyzer. The DMM has its own driver, and so forth. And the test program is talking through the driver to the different instruments. In a synthetic instruments approach, you have your DUT in the bottom, but it's connected to generic synthesis hardware and generic acquisition hardware. And all of the specific measurements are done in your software, and the test program is only handling the different test cases and collecting the results. So some ways in why this is interesting: you have in the virtual instrument setting, you have the raw data is by default, usually it's hidden from the developer. It's inside of the instrument or the driver. Well, for a synthetic instrument, the raw data is what we're working on. That's where we start our journey. We do all different types of measurements on the same raw data. No matter if it's a frequency domain or a time domain measurement, we still use it on the same raw data. In the virtual instruments setting, the algorithms are also hidden in the instrument or in the driver. Don't necessarily know how the spectrum analyzer is getting the frequency response, and sometimes you don't want to, but sometimes you want to do that. While in a synthetic instrument, the algorithm is the instrument. And there's also a difference in how you perform the test program. So when you're doing your tests for a virtual instrument, you have separated measurements. So say you want to do a third order interception points measurement. You want to control a spectrum analyzer, a power meter, and a signal generator. You will, in your test program, make your test where you continuously add power to the signal generator to see where the curve starts to decline. While in a synthetic instrument, you would try to go as far as possible in making the measurement software more integrated. So you would have the IP3 measurement in the measurement software, and the test program will only ask for check IP3. So that is the more on a very high level distinction between the two. So when do I think it's probably it's a good thing to start thinking about having a synthetic instrument? I think when your test system is having a very long life cycle, you're not depending on the vendor or the oscilloscope to keep the functions you're actually using for all of the future versions of the same oscilloscope. For as long as the generic hardware is generating the raw data in the same format as your software is using it, it doesn't really matter what is collecting the data. Then obviously minimizing footprint is one of the things as well, as the more different things you can do with the same set of hardware, the smaller your systems gets. I can also think that you can optimize performance. As you're in control of the whole system, you can really leverage parallelism that LabVIEW and especially FPGAs are very good at. You can really use the parallelism in your systems. You can also use multiplexing, and I'm going to show an example of how to do that to enable you to make more measurements in the same time at the same given time. And then especially for tailored measurement functions, you might have a very specific video protocol you're using. You have your own. You might of course get that to work with a regular oscilloscope or something, but as soon as the new oscilloscope is coming out, or you need to change to another vendor, you might have a risk of the driver not working the same way you thought, and you can't change to anything, to just whatever else. And then something we actually tested was to replace a legacy instrumentation. So I had the privilege of leading a team, and we developed a synthetic instrument platform, and we made two specific instruments. One, a rather high-end microwave tester, and the other we tried the same platform on was to replace a low-frequency instrument that we had been using for years. I think it was released in the late 60s, and we really used like two corner cases, very odd functions that it had. And I guess we've been lucky that the instrument was still around, and I checked yesterday and it's actually still around. But when you're designing a test system that you think the test system is going to live for 30 years, so thinking that instrument will, apart from the already 40 years it had before, it's going to live another 30, it's quite optimistic. So what we tried was to replace that with a synthetic one. And we not only replaced the measurement functionality of it, we also replaced the communication protocol. So the old one was using a GPIB and talking through VISA from the test system. So we implemented VXI 11 on our synthetic instrument. So the old test system didn't really know that it was another instrument connected to it. So we didn't have to change anything in the software platform or any configurations at all on the legacy test system. But that's also a nice use case of it. So going more into some technical details, I think the most common architecture I've seen around is the CCC architecture, so controller, codec, and conditioner. On the upper hand, you have your synthesis workflow where you send the signals to your device on the test. and the lower hand you have your analysis flow. And the controller is where most things are happening. That's where you have your DSP, your FPGA, or your software, the things that make the personality of your measurements system. The codec, the only two examples I've found is an AD converter or DA converter, depending on which direction you're going. While on the conditioner side, there's a vast majority of, or variation of things you can add to it. So anything that would condition your signals to wherever you're sending it to on your DUT. So in an RF setting, you might be needing some up or down converters, and you have filters, you have muxes and switches, and yeah, a lot of things. So why do we want to have generic and non-specific hardware? Well, the most obvious thing is, well, it's easy to replace the hardware. If we're not using anything that's specific for a vendor or for a specific instrument, we're just collecting the data, then we can use more or less, of course, any hardware to use the same thing. We can also adapt the system to the use case. So that's what I'm talking about before. So if you need more accuracy, you can change the hardware to a more capable AD converter. If you want something cheaper or smaller, you can use something else, something much cheaper, but you're still using the same software in the background for measurements and functions. Also, an interesting thing there, I think, is that you can do a variety of different measurements on this exact same raw data. So no matter if you're doing frequency domain or time domain measurements or analyzing video signals, still using the same raw data. And one of the examples where that is really interesting is when you're finding a spur or something in your signal in a spectrum analyzer, but it's very intermittent, so you don't really see when it's coming, and you would like to see that on your oscilloscope as well. It can be quite tricky with a traditional approach to actually measure on the same raw data, because if it's not apparent appearing on the spectrum analyzer when you do your acquisition on the oscilloscope, well, you're not going to see it. But in a synthetic instrument, you would do it on the same raw data. So if you see it in the spectrum analysis, well, you can analyze the same on the same data. So why do we want raw data? I think most of you want to save all your raw data. That otherwise you might not do all of these things, but some of the things are really interesting, I think. You can add measurements to already performed tests. So if you have already produced 10 or maybe 100 of your units and shipped them, and then you realize, oh, maybe we should have measured harmonic distortion on these. And if you've saved your raw data, you can actually add the measurements to already performed tests. That might be a validation do we really need to check the harmonic distortion? If we don't have any issues, we don't have to add any tests to the production line. And then I've said already the interchangeability of hardware. Another use case that I've seen, that I've actually encountered. In this case, I've drawn a intermodulation distortion measurement. I don't think that's what we actually did in practice, but we had something where we stored the raw data. But say you do your IMD measurements in production, you ship your 100 units into the field, and some of them are coming back. after some investigation, you see that some of your products, they have an extra frequency higher up in the frequency range than what you did the actual measurement. And that is the thing that causes the issue. And there might be a production flow or something, or components into your product that might be working differently between different batches or something. And then you can go back through the raw data from previous tests and you can find out which serial numbers have this issue. So when you're recalling your products, you only need to recall the ones who actually have this flaw and not having to recall everything. So I'm going to go through a few ways of shrinking a system in size. The first one is using time domain multiplexing. So for example, if you're measuring temperatures on an engine, you might want to have very accurate measurements, but the rate of change on the different signals are very slow. So you don't have to have a very high sampling rate to follow what's happening. One way to do that is to have a commutator that goes through the different switches through the different temperature sensors and take one sample at each of the different pinouts on your DUT, then starting over from the top. So if you see this, so the first sample is going to the green signal, second to the red, third to the blue, and then you're starting over green, red, blue, green, red, blue. Then obviously afterwards you have to sort these into the different signals. But if you have an AD converter with a sampling rate that is well above Nyquist for all of the different components, all the different signals you're measuring on, you can make quite a few measurements using one single AD converter, and then you can have that as a very high precision one. But you only need one. Another way of shrinking a system is by frequency domain multiplexing. So if you're measuring on very narrow band signals and you have a very wide band AD converter, you can mix each of the signals with, I would say, their own baseband frequency, and obviously separated enough so you can distinguish them. Mix them together and sample, and when you get into your analysis stage, you filter out the different components and perform your FFT, your measurement functions, the ones you want on them. And that's also a way of using a high performance AD converter and making loads of measurements. Another way to make a system smaller, maybe not necessarily a synthetic instrument approach, but a way to make it smaller is to leverage FPGA IP. And one example is using different communication protocols. You don't use them at the same time. You can use a flex Rio or a compact Rio and then an adapter to it, and you have your ports and your pinouts. Depending on the application, you load the FPGA with the IP you're using. So instead of having 3 cards, one for RS, one for CAN, and one for I2C, you have only one card. And that's also something I've used a few times. I think think it's quite a nice way of using the space you have. So I'm gonna more or less wrap it up here, but it's got a bit quicker than I thought. So I was thinking yesterday, I gonna talk to a LabVIEW group. I need to add the LabVIEW aspect to it. And when we made the synthetic instrument platform, we used LabVIEW. That was one of the cases I would bring up in my version of the presentation on keeping it simple. I'm actually going to take the blame myself. I chose Active Framework as the main architecture for the platform, and technically it worked very well. It performed really nice. It takes a bit of time to get your head around the concept of the Active Framework, but once you have it, it's very nice. But in that phrase, you have the issue. It takes a bit of time to get your head around it. And you need to make some thought onto the team you have, what capabilities you have, and what the team I was working on were hardly even programmers. It was more like electronic engineers, and the concept was very hard to maintain or to leave it to someone else. So I think that is one of the things I learned, that you should actually try to make something simpler, so that's simpler to understand if it's possible. It's not always it's possible. So I was thinking a bit yesterday on how I would do it today if I would do the same thing. I think I was still for the controller side, so where I have all my measurements, algorithms, controlling the hardware, collecting test data, all of those parts, I would still use LabVIEW, probably LabVIEW real-time and FPGA as well, as we did the last time. But after seeing Danielle Job's presentation on the first GDevCon on using LabVIEW with JavaScript and Python, I would probably put the GUI in JavaScript, because I've tested a few times since then, and it's you can really see that LabVIEW is wonderful for controlling things, but on a GUI perspective, it's quite cumbersome, while JavaScript is very reactive and forgiving. So that's probably the way I would go about things if I would do this once again. That's pretty much sums up what I was talking about. So if you have any questions, I'm happy to try to answer them.
Thanks very much, Fred. Really appreciate that. That was interesting insight into things. Has anyone got any questions?
It was confusing enough.
Bruce, you go for it. Take yourself off mute and ask away.
I was wondering if there were problems when you are muting the signals, if you have problems with crosstalk.
Yeah, sometimes you do. You need to separate them quite widely, and I guess you're talking about the frequency domain multiplexing, and I think if you want really high precision, you might not go for the frequency domain multiplexing thing. It's more if you don't have as high precision measurements to do, I think. We didn't see too much crosstalk, but some, if you have a higher, if they were too close or on harmonics of each other, we could see some crosstalk. That's not too bad. Better than we thought.
Thanks.
Fred, there's a question in the chat as well. Don't know if you can see that.
Where do I see this chat?
It's
there. So is that so how different the synthetic instruments with the IVI foundation drivers? Well, the IVI foundation drivers, you're still very focused on one type of measurements or instrument rather. So you have your IVI for a function generator. It will always only work with a function generator, while a synthetic instrument is working higher up, so to speak, using the raw data, not specifically using it for function generation.
Does that answer the question?
Yes, thank you.
Awesome.
No, thank you.
David, you got a question? Go for it.
I was wondering how you went about getting this either calibrated or signed off. I know I've had customers in the past that have gone, everything on my ATE must be calibratable, it must go to an external house. And this method sounds really interesting, but I was wondering if you ever had that problems and how you overcome them.
Yeah, we had a lot of discussions on that. So one side is obviously calibrating the hardware, so make sure we know how that performs in calibrating the raw data. But the other part, we actually made the calibration specific for each measurement. So if you're going to do a IP3 measurement, you made a calibration before making the measurement. And it's quite commonplace if you do microwave measurements, you usually do a calibration before each of your measurements anyway. But yeah, that is an interesting point, and something that needs a lot of thinking depending on the application you're using it for, how much that's affecting your system.
So it sounds like you just need to get management and higher ups buy-in before you attempt it.
Yeah, you have to have a good you have to prove your case in a good way, I think.
Cheers. Thanks very much.
All right, Craig.
Hi, Fred.
Hi.
Just to add to the calibration question, really. I mean, the majority of calibration is done as a system cal. So you're inserting a signal and you're expecting a calibrated signal back. With the generic hardware, how do you prove that there isn't any drift in terms of the data you're requiring, the raw data? So you can start with a cal, a gold standard calibration, but how do you know that none of the system accumulation errors drift across time?
I guess you would do that more or less the same way as you do in a normal. You need to save your calibration results and have follow-ups on what's happening over time.
Okay, so if you was, for instance, I mean, the whole idea is that you keep the hardware generic, and you can swap in and out instruments as and when. How would you go about deciding the behavior of a new instrument compared to one you're replacing on that specific channel, for instance?
Yeah, I wouldn't say you would hot swap your hardware, same test system or the same application you're using it for, or maybe between, if you're making a new test system, or you need to upgrade your old test system, then you're more in the choice of hardware. It's not that you change hardware during the course of actually using the system, if that makes sense.
Yeah, so your algorithms actually get developed as part of your synthetic instrument. If you need to add stuff, it gets done in there.
Yeah.
Ah, okay, cool. Yeah, that answers my question.
Oh, good.
Nice one. And Leah?
Yeah, I just want to say thanks for the presentation, Fred. I've just got a short question, which is, you said that the synthetic instruments can be a lot smaller. I was just wondering, in the end, how much smaller your two instruments were compared to what you were working with before?
Yeah. As well, the first one, the one we replaced, the legacy instrument, it wasn't that much smaller because it was only one instrument, but it was made in 2 PXI cards instead of whole rack.
Sure.
The other one, I think it was like a full 99-inch rack that we replaced with a PXI chassis. So.
Oh wow! Yeah, that's quite a reduction.
Quite a bit. I'll change there.
Thanks. Oh, and just quickly, can anyone else not see the chat? I might have to come out and back in again because, yeah, it's not there for me anyway.
Just me. I can see the chat at least.
Okay, I'll try rejoining. Thank you.
Awesome. And Neil.
Yeah. Hi. Thanks, Fred. That was a great presentation. I think you mentioned, if I heard you right, that you were brave enough to try Active Framework on RT.
Yeah.
That deserves an applause just for that by itself. I had a lot of problems recently, or just basically forever, with RT throwing random deploy errors. Like when you've changed something as part of a class private data and it just refuses to deploy with some random error messages, and you have to do things like mass compile and rename classes and VIs and stuff like that. I would have thought that with the Active Framework, especially as it's class heavy, we'd have lots of problems like that. Is it just me, or what was your experience with that?
We didn't have a lot of issues. We had some issues with we were trying like a plugin architecture where you would have classes on disk and just look through the disk to see what algorithms I think we were using, and depending on what platform we would deploy on, that would be handled very, very strangely sometimes. So we had one system with a VxWorks RT, and the other ones was a Linux RT, and it would only deploy on one or work on one, because on the other one the file system was working in a completely different way. I don't remember how we what workaround we found to that, but I had a discussion with someone on LinkedIn a couple of weeks ago about that, and they had a very nice solution for it. So I can.
You said use Python.
No, that was not the solution. And definitely not my solution.
Yep.
There was a couple of comments in the chat that
it's good to know.
There was a couple of comments in the chat that are picking up on that point. So if you can see the chat, check those out.
Yeah, I feel like I can try to browse through my LinkedIn to see who talked about it. I can't remember who I was talking about this. But I had some quite nice insights on that.
Awesome. Good stuff. Any other questions before Fred wraps up and finishes? Don't think so. All right. Thanks very much, Fred, for that. Really appreciate it. And
yeah, thank you.
You'll be back again.
Yeah, and anyone feel free to reach out on LinkedIn if you want to have a chat about something. I'm
Yeah,
rather active there as well.
good stuff.
Hopefully not too many of you clicked on the link to my webpage. I'm not very active there.
No worries.
Okay, so thank you for listening, and I leave